Yeah.
Okay, I believe it is working. We're starting class now with Claire and Lucy and Kyle, who aren't here. And we've been very serious up to this point. We haven't made any jokes or anything. So we're starting now with concave mirror again, shiny on the inside of the curve. That's the vertex. This is the principal axis. These are terms that you now know. This is the center of the sphere. So halfway between here and here would be the focal point. And then this distance from the vertex to the focal point is the focal length. Okay. You also know the mirror equation, which is 1 over f is equal to 1 over psi plus 1 over so. You know that, and we're able to use that when you did your homework. Also, you know the magnification equation, which is a ratio of high to ho. It's just the ratio of the image height to the object height. Now, you may have noticed in your book, and I don't think I mentioned yesterday, that this ratio of heights is the same ratio as the distances. And so high over ho equals negative psi over so. All right, and if I didn't mention that yesterday, sorry, but it is in your textbook, but I'm mentioning it now. Now, psi is the distance from the mirror to the image. So is the distance from the mirror to the object. There's a negative sign here, which is important because the signs of all of this are important. If you calculate, here, let's talk about m for a while. If you calculate m and you find it's greater than 1, then the image is what? What does that mean? The image is bigger than the object. The distance to the image would be greater than the distance to the object. So we did this yesterday where you had an object right here and the image was way down here and it was larger, but it was inverted, but it was also farther away. See, that distance is SO, and the distance from here to there is SI. Okay? Now, the negative is there because if you divide SI by SO, those are both positive numbers. I'm not sure we talked about how S can be negative, but we will in just a second. But right now, they're both positive numbers, and yet the image is upside down. So in this case, in this example, m would come out to be a negative number, and it would be more than 1. I just made up a number. But it's got to be more than 1 because it's bigger, but negative means it's upside down.
So it's the absolute value. It shows how big it is.
Well, both heights are positive. No. Yeah. If either of these is upside down, it's negative. Yeah. So in this case, the HI is negative because it's upside down. The HO is positive because it's upright. So if you divide those, you'll get a negative number because that's upside down. These are both positive numbers, so the negative's in the equation. So if you calculate it that way, you'll still get a negative number. So either way, you get the negative number. Okay? That's why the negative is there. It works. If you had an image that was upright, then both of these are positive. M would be positive. And one of these would be negative, so that the negative made positive. And that's what we haven't talked about yet. How can SI be negative? So I'll just go ahead and tell you since we've mentioned it. SO is always pretty much going to be positive. When do you start out with an object that's upside down? I don't know.
Monkey bars.
You don't. But SI is positive when it's in front of the mirror. When the image is on the same side as the shiny part of the mirror, like it is in my example here. SI is positive. SI is negative when it's behind the mirror. If the image was back here, like it was in a plane mirror, it was behind, that would be negative. The SI would be negative in a plane mirror. Okay, here it's positive because the image is not behind the mirror. Okay, so that's pretty easy to keep up with the sign. The sign's important because, and the sinus equation makes it work. If SI was behind the mirror, then when you divided this, you would add a positive number. Now we're going to look at an example where SI is behind the mirror in just a second. But right here it was in front of the mirror and it's real. Okay, so images, can either be real or virtual. You need to know the difference. Images can have, can be larger or they can be smaller than the object. Here it was larger. It is possible to get an image that's smaller. We'll look at that. Images could have a magnification that's greater than 1 or it could be less than 1. If the image is smaller, it's less than 1. Yeah. I don't know. For these S's and for F, this is true. If F is ever behind the mirror, it's negative. Can F be behind the mirror? Can F be behind the mirror? It would be if what? If it's convex.
Oh my God!
When we get the convex mirrors, F is a negative number. Same mirror equation, but F would be negative. Yeah. All right. So what I want to do now is go back and look at some more examples for the concave mirror before we go to the convex mirror. Let's put the object in different places. So far, you saw that if I put the object between C and F, the image is going to be behind C and it's going to be bigger and it's going to be inverted. Okay. Now let's move the object to where the object is behind C. Now you have to be able to draw the Freebody diagrams, so I'm not going to do that with blue, so you'll remember it. The first incident ray goes from the top of the object parallel to the principal axis and it hits the mirror. And anything that goes in parallel reflects through the focal point. Use a ruler when you do this on your own so that the lines really are straight. What would be perfect would be if you did it on graph paper. Because then, you make these right along the lines of the graph paper. Okay. Now that's the first one. The second one goes from the top of the object through F. Straight line right through F and make it straight. And it reflects parallel. I don't think I did that very well. This is why you use a ruler, which I'm not doing. And so I apologize. Boom. And it reflects parallel, something like that. Okay, the third one I told you, the one I usually use for third is I go from here to the vertex. Straight line to the vertex. I missed the vertex. Vertex. And that angle has to be equal to this angle, law of reflection. But if they are, then this would go through the same point. All three would converge at the same point. And okay, that's all I'm going to do. So that means that's where the image is.
How big is it?
Now, this one, I should have made it a bigger difference, but further out. But this one is supposed to be smaller. It's a little bit smaller, but it's not much smaller. It should be smaller, and it should be between C and F. And it should still be inverted. It's still real because these are actual light rays converging to form it. So if you put a screen right here, there'd be an upside down image of the person. It's a real image.
Okay.
Okay, so that's real. It's inverted. It is smaller, and it's between C and F. There you go, between C and F. That's when the object is out beyond C. So look at what we did. When we put the object here, the image was there. When we put the object here, the image is there. You see that? Put the object between C and F, the image is back here. Put the object back here, the image is between C and F. And that will always be true. Okay. Everybody get that? Now you could, again, use this to calculate whatever you want to know. You can solve that for SI and get this actual distance here. If you know F and you know so, distance to the object. You could use this to get magnification. If you know either of these or these. If you know both of these, you can get magnification that way. Sometimes the question will be, well, how tall is the image? And if you've already gotten these numbers, you've got M, you can solve that for this if you know each of. Okay, so that's that. Now, what if the object is right at C? What if you put the object not in front of C, like our first example here, not behind C, but you put the object right here at C? Where's the image going to be, do you think?
At C.
Yeah, if you did this, you got that, this, you got that, here you're going to get that. It will be upside down now. And if we draw the lines kind of hurriedly, there's parallel. Where did my F go? That's C, so F is about there. All right, that reflects through F. If it goes from the head through F, it reflects parallel. If it goes from the head to the vertex, it reflects so that those angles are the same. They all converge here, which should be at C, the same height, but inverted. And it's real because it's being formed by actual reflected light rays. Okay, so real inverted, but same size, and but inverted. So you should have in your head, you should already know that if the object's here, the image is there and bigger. If the object is here, the image is there and smaller. If the object here, the image is there and the same size. Okay. Now, there's two more questions with this one. What if I put the object at F? What if I put the object, there's C, the center. Here's the focal point. What if I put the object right at the focal point? Where do you think the image would be then?
Oh.
Do you remember looking at your mirrors? What did you
Oh my
see
gosh,
when the
it's
mirror was
right
at
side
F?
up now?
You saw nothing. It was just all blurred.
Oh,
There is no
now
image.
it's really good.
That's the point where there is no image.
The light is all just white. Where's the light
Now,
coming
you
from?
remember back here, you saw yourself upside down, didn't you?
Yeah.
And every time we've drawn one, it was inverted. What did you see when you held it right here, blur? Nothing. What about when you moved it in?
Wait, but why does it get blurry?
It wasn't so blurry when you moved it close. You saw your nose or your eye. And it was what? Was it upside down?
No, it wasn't.
It was magnified.
It was bigger
Mm-hmm.
and it was upright, wasn't it? Not inverted. So let's put the object inside and see if we can draw the diagram that will show us that. We're still going to obey the same rules. The rules are, if you go from the top of the object parallel, and if it goes in parallel, you know it's going to reflect through F.
Oh, that's wild.
The second one goes from the head through F. Well, F's behind it. How do I do that? I get a ruler and I line up the head with F, and it goes up like that.
It goes up like
But if it's lined up with F, it's going to reflect how?
that.
Parallel. Those rays are never going to converge, are they? And if I draw the third one from here to the vertex, and I make it have, that doesn't look equal. If I make it have equal angles, it's never going to converge either. These are diverging rays.
Yeah.
But if you have an image, they have to converge somewhere.
So your image is what?
The image is behind it. You take these reflected rays, make sure you're taking the reflected rays, not the incident ray, and back them up. Take this reflected ray and back it up. Take this reflected ray and back it up. They did not hit the same place, but they should. There you go, like that. They converge back here. And where they converge is the head, so look. There's my image. See, it's bigger. This is what you looked at when you looked at your eye in the mirror. The image was bigger than the actual object, but it was upright. See, that's not upside down, is it? Now, is that a real image? No, it's behind the mirror. There's no light. These blue lines are not light. See, the actual reflected rays are diverging. They're not going to form an image. Real images is when the reflected rays converge. That's a real image. You can put a screen there. Well, there's nowhere to put a screen here. They're converging back here where there is no light. So yeah, if you set up a screen there, is there an image on it? No, it's in the dark back behind the mirror. But when you're looking into the mirror, that's what you see. And it looks like it's the images behind the mirror, just like a plane mirror. Only with a plane mirror, they're the same size. Here it's actually bigger. Okay, now would that work in our equation up here? Yes. SI would come out to be, what do you think? A positive or a negative number? Negative. SI would, if you just put in F, whatever F is, and put in so, which is less than F, because it's in front of F, that's going to be a negative number when you solve it for SI, which means it's behind the mirror. It really would work. When you use this equation over here, M is going to be positive or negative. Which one? M, for that image there. It's going to be positive. HI and HO are both upright. So that's going to be positive. Over here, SI is a negative number, but the equation has a negative in front of it. It becomes positive. So M is a positive number when it's upright. M is a negative number when the image is inverted. Okay. So the equations all work, no matter where you put the object. But you need to know how to draw the diagrams for the different positions. And also drawing the diagrams can help you know what you're supposed to get. All right, so you already know if the object's here, the image is there and bigger. If the object is back here, the image is here and smaller. If the object is here, the image is there, same size, still inverted though. Those are all real images. But if the object is inside of F, the image will be behind the mirror, virtual image, larger, upright. Okay. Now you're just learning this yesterday and today. But all those things I just said are things that you should be able to pull out of your head. Then when you do the math, that confirms it, but you need to, it will help you on a test if you already know what to expect. And put the object here, you already know where the image is going to be about. Okay? Now, we want to look at a convex mirror.
Yeah, we do. It's gonna be insane.
Convex mirror. You all had convex mirrors on your homework, and you had to actually read the book to figure out how to do it, didn't you? Is that what you did? Read the book? You already read the book because you'd taken notes, I think. I'm going to do it this way. By the way, all my diagrams pretty much have a shiny side going on the left side of the mirror, and the object is over here somewhere. On a test, they could reverse it, so don't get too used to it. You know, they could give you they could make this be the shiny side over here, and the object's over there. So don't get too confused if they switch the mirror around. I'll try to switch it once in a while up here. But right now, the shiny side is now on this side. Convex mirror. Okay, back here to behind the mirror is dark. Over here is the shiny side, so the rays are going to go from the object and reflect back. Now, where's the center of this circle, or the sphere? The center of the sphere is back here, isn't it? Which means there's a focal point here. And that's the focal length, which would be a negative number. Negative something. By the way, you don't have to use SI units when you're dealing with things like this. If that's centimeters, that could be centimeters, and that's centimeters. As long as they're all the same unit, you don't have to convert things to meters because they're all the same. Okay, back to this. Let's draw the ray diagram. Ray diagram works the same if you can adjust it to this situation. So top of the object, parallel, it goes toward the mirror and it strikes the mirror. What's the rule? If it goes in parallel, it reflects through what? Through the focal point. Well, the focal point's over here. So you take your ruler and line it up, and it's going to reflect that way. Okay. The second one we said goes from the head through F. Well, F's on the other side, but that means you need to take your ruler and line it up with F so that it hits the mirror about there, where if it did keep going straight, it would hit F. You've lined it up with F. See what we did? Now, what's the rule? If it goes in through F, it reflects where? Parallel. That one's going to come straight back parallel to the principal axis. And you can clearly see these are diverging rays. This convex mirror is also called a diverging mirror. It's a diverging mirror because the rays diverge, they spread apart. The third one, once again, I would go from here to the vertex. And, whoops, where's the vertex? The vertex is down here. Okay, so I'm going to go to the vertex, and it's going to reflect obeying the law of reflection. The angles are the same. And once again, all three reflected rays are diverging. You don't have an image anywhere over here. Where's the image? Behind the mirror. So, back up. The reflected rays, not the incident. You got lines all over, so be careful. You want to take the ones that reflected. All right, that one was reflected, so I back it up and I get a line like that. And this one was incident. No, this one was incident. That parallel one was reflected, so back it up. Make sure you're getting the reflected rays. Back them up. That one is a reflected ray, so back it up, and they should all converge at one point. There is the image.
It's so small.
The image is behind the mirror. So, is it real? No. What is it?
It's virtual.
Virtual. There are no actual light rays back here. Behind the mirror is dark. So, not real, but the screen there, nothing's on it. However, when you look in the mirror, you see an image that looks like it's behind the mirror, but it's smaller.
Yeah.
But it is upright also. Not inverted, upright. So HI is a positive number because it's upright. HI. SI is negative because it's behind the mirror. F would be negative too, it's behind the mirror. But SI is behind the mirror. That would come out negative just like that does, even though SO is positive. SO is always going to be in front of the mirror or nothing happens. So that's a positive number, but both of these are negative now. They would come out to be negative if you just do the math. M. What's true about the magnification of this mirror? Is it greater than 1 here, or is it less than 1? It's less than 1. The image is smaller. And the SI is less than the SO. See that? SI is less also. So in our magnification equation where it's high over ho equals negative psi over so. An equal sign. Got too many bars. The SI is negative, but there's a negative in the equation, so when you divide it, you get a positive number. The HI and HO are both positive because they're both upright. That will give you a positive M. M is positive, but it would be less than 1 because HI is smaller. SI is smaller as well. So M is less than 1, but positive number. Now, you think you see how to do this? Because I'm going to now hand you a convex mirror to look at. The other day you had a concave mirror you looked at. I'm going to give you a little convex mirror. While they're looking at that, we're going to pause this. Ooh, which one is the pause button? The one up there?
Yes.
All right, we're doing this for you, Claire, Lucy, and Kyle. This is a convex mirror.
Day 100 something.
Whoa.
100.
Yeah.
We're
Okay.
so close to having 100 days left of school. Or left in
You,
general.
you all realize that your conversation about days of school is going to be viewed by people in Poland?
Yeah.
Well, of course.
Okay.
Hey guys, in Poland, we only have 150 days left. I've been on the whole time.
All right, we are resuming homework number 14. The
What number
answer
is it?
is 7.64 centimeters. That's the height of the image.
Two answers on 14.
Oh, I'm sorry. The height of, yeah, thank you. That's the height of the image, whichever question that was. The other question was the distance to the image, SI, and that is negative 28 centimeters. This is a problem where the object is a concave mirror, but the object is inside of F. We did one like that. And when the object is inside of F, you know the image is going to be behind the mirror and larger and upright. So SI comes out negative because it's behind the mirror. HI comes out positive because it's upright. But if you just plug numbers in correctly to the equation, you'll get the right sign. Okay? That's 14. Now, were there any other even numbered problems? No? Or were there?
24.
24? Did I give you 24? The answer to 24 is 74 centimeters. That's SO. You had to find SO that time. And it's positive. SO is pretty much always positive. 74 centimeters. Okay. Is there one we need to work to finish out the class? Or should I give you time to work on focus questions?
I'd like that, but
Can you do 21?
21. We can do 21. Is someone going to read 21 to me?
Oh,
He has the book open. Jaden has the book open.
I would rather do one problem. So yeah, let's do
Hey
21.
Jaden, can you read 21?
These are a bunch of wimps, Sarah. They don't like reading problems. I had a question, and now I don't know what it is, which is sad. But, here we are.
All right. Are you going to read, Sophia?
I
Or is
sure
Jaden
am.
going to read?
Oh, no. This is my job.
Okay.
A
Go.
concave mirror, R equals 56 centimeters. Oh, wait, this is 21. Yeah, yes, you said 21. Okay, 56 centimeters is used to project a transparent slide onto a wall. The slide is located at a distance of 31 centimeters from the mirror, and a small flashlight shines light through the slide and onto the mirror. The setup is similar to that in figure 25.18a.
Okay.
Part A. How far from the wall should the mirror be located? B. The height of the object on the slide is 0.95 centimeters. What is the height of the image? And part C. How should the slide be oriented so that the picture on the wall looks normal? And now I remember my question. Are we ever going to do any problems with mirrors that are like 3D? Where you have to be like, light going everywhere.
I don't think so.
Okay.
All right. If the radius is 56, then half of that's 28, which is the focal length. You had to do that. So now you know for this mirror equation, you've got 1 over 28 to start with. And I think the image is the one the object they told us was 31. So 1 over psi plus 1 over so, and so is 31. This object here is 31 centimeters away. So it's further out than F, but it's not as far as the center. Therefore, you know that you already know the image should end up back here somewhere and upside down and larger. Now, the answer, though, to A, if you solve that for SI, is 289 centimeters. You can just keep centimeters for everything, which means the image is going to be way back here somewhere, pretty far. If you drew the ray diagram carefully, more carefully than I'm doing, you would see they don't cross till way back here somewhere. Okay. B is asking for the height of the image. The height of the image is back here somewhere. You know it's going to be bigger than the height of the object. You also know it should end up negative because it's upside down. All right, so if I use my magnification equation, it's high over ho, and I'm looking for high, and that's equal to negative psi over so, and I know psi and so both now, so that's calculated as negative 289 divided by 31. Okay, and that's equal to high over 0.95. They told you that the object was 0.95 tall. And if you solve that for HI, you get negative number 8.9. HI equals negative 8.9. Always look and see if it makes sense. You know HI should be HI should be much more than the 0.95. It should be a whole lot bigger. But also it should be negative because it's upside down. And when you just plug into that equation, you do get a negative number that's more than 0.89. Okay, C, what was C?
It was, how should the slide be oriented so that the picture on the wall looks normal?
Oh yeah, this is actually a slide, like on a slide projector. Do you all know what a slide projector is?
Yeah.
They used to make these little slides
You could see from
surrounded by a cardboard thing, and you would stick it into a projector machine and it would flash it up on a screen. Okay, well, it inverts. The image is inverted, so how should you put the slide in? Upside down. And slide projectors, I used to use them occasionally, and yeah, you always had to put the slides in upside down.
And
then the image on the screen would be upright.
You said to your physics students, look, you demonstrated that.
I could explain, you know why you have to put the slides in upside down? And I'd start drawing diagrams.
They'd be like, Mr.
They would all
Clausen,
walk out of the room.
we're learning about
Okay.
mechanical motion.
That's the end of our recorded class. I'm going to turn this off. Nice to see all of you today, or whatever day you watch this. Hello to those of you in Poland. Hope you speak English, and I will see you later. Bye.